Download this code from codegive.com, link in the description below. OK, let's dive deep into error analysis, a crucial topic for MHT set and other competitive exams. We'll cover the theoretical underpinnings, common error types, strategies for solving problems, and provide plenty of code examples in Python to illustrate these concepts. Introduction to error analysis. In scientific measurements and calculations, it's virtually impossible to obtain a perfectly accurate result. There's always some degree of uncertainty. Error analysis is the process of quantifying and understanding these uncertainties to assess the reliability of experimental results. It helps us to estimate the accuracy and precision of measurements. Determine the reliability of a result. Identify sources of error. Improve experimental design and procedures. Propagate errors through calculations. 2. Key terminology. Before we proceed, let's define some essential terms. Accuracy. How close a measurement is to the true or accepted value. A high accuracy measurement is close to the real value. We often express accuracy in terms of percent error. Precision. How close multiple measurements are to each other. High precision means the measurements are consistent. Precision is often described in terms of standard deviation or range. Error. The difference between the measured value and the true value. Error can be positive or negative. Error equals measured value, true value. Uncertainty. A range of values within which the true value is likely to lie. Uncertainty expresses the potential error in a measurement. It's usually denoted as plus or minus delta x, where delta x is the uncertainty. Absolute error. The magnitude of the difference between the measured value and the true value, i.e., the absolute value of the error. Absolute error equals measured value, true value. Relative error, or fractional error. The absolute error divided by the true value. Often expressed as a percentage. Relative error equals absolute error / true value. Percent error equals absolute error / true value, 100%. Systematic error. A consistent error that occurs in the same direction each time. It can be caused by faulty equipment, calibration issues, or a consistent bias in the measurement technique. Systematic errors affect accuracy. Examples: a miscalibrated scale, a parallax error in reading a meter, a zero error. Random error. An unpredictable error that varies randomly from one measurement to another. It can be caused by fluctuations in environmental conditions, limitations in human observation, or inherent variability in the sample. Random errors affect precision. Examples: small variations in temperature, slight variations in how a person reads a measuring instrument. Least count. The smallest value that can be accurately measured by an instrument. The accuracy of a measurement is often limited by the least count. 3. Types of errors and their sources. Let's explore the different types of errors in more detail. 1. Systematic errors. Instrumental errors. Arise from imperfections or miscalibration of instruments. Example: a faulty voltmeter that consistently reads 0.1 V higher than the actual voltage. Environmental errors. Caused by changes in environmental conditions like temperature, pressure, or humidity that affect the measurement. Example: expansion of a metal ruler due to changes in temperature, leading to inaccurate length measurements. Observational errors. Due to errors in the observer's technique or bias. Example: parallax error, reading an instrument from an angle. Asterisk theoretical errors asterisk due to simplifications or approximations in the theory used to analyze the data. Asterisk example, ignoring air resistance in a physics experiment. 2 random errors asterisk. Asterisk fluctuations asterisk random variations in readings due to uncontrolled factors. Asterisk human error asterisk slight inconsistencies in how a person takes a measurement, example judging the position of a pointer on a scale. Asterisk statistical fluctuations asterisk inherent randomness in the process being measured, example radioactive decay. 3 gross errors asterisk. Asterisk these are large, easily identifiable mistakes. They are often caused by carelessness or misreading of instruments. They should be eliminated by careful observation. Asterisk example, reading a value from a meter incorrectly, recording the wrong units. 4. Propagation of errors. Often, we don't just have single measurements, we perform calculations using multiple measurements, each with its own uncertainty. We need to know how these uncertainties combine to affect the final result. This is called error propagation. Let x and y be 2 measured quantities with uncertainties delta x and delta y, respectively, and let z be a function of x and y. Here are the common rules for error propagation. 1. Addition and subtraction asterisk. If z equals x plus y or z equals x, y, then delta z equals square root, delta x, superscript 2 plus, delta y, superscript 2, add uncertainties in quadrature. 2. Multiplication and division asterisk. If z equals x asterisk y or z equals x slash y, then, delta z slash z, equals square root, delta x slash x, superscript 2 plus, delta y slash y, superscript 2, add relative uncertainties in quadrature. 3. Power rule asterisk. If z equals x, then, delta z slash z, equals n asterisk, delta x slash x. 4. Constant multiplication asterisk. If z equals k asterisk x, where k is a constant, then delta z equals k asterisk delta x. Important note asterisk these rules assume that the errors in x and y are random and independent. If the errors are systematic or correlated, the error propagation becomes more complex. V. Numerical examples and code, Python. Let's illustrate these concepts with some examples and Python code using the uncertainties library. This library makes error propagation much easier to handle. Installation asterisk. If you don't have the uncertainties library, you can install it using pip. Explanation of the code asterisk. Asterisk a float, value, uncertainty, creates an object that represents a number with an associated uncertainty. Asterisk the library handles all the error propagation calculations for you automatically when you perform arithmetic operations on a float objects. Asterisk uncertainties.u math imports versions of standard math functions, like sin, cos, sqrt, that are compatible with a float objects and correctly propagate uncertainties. 6. Strategies for error analysis problems, MHT set focus. 1. Identify the types of errors asterisk determine whether the errors are systematic, random, or a combination of both. This will guide your approach. 2. Understand the formulas asterisk know the error propagation formulas for common operations, addition, subtraction, multiplication, division, powers. 3. Use the right tools asterisk for complex calculations, using a library like uncertainties in Python is highly recommended. However, for simpler problems on the MHT set, you may need to apply the formulas directly. 4. Pay attention to units asterisk ensure that all quantities are expressed in consistent units before performing calculations. 5 significant figures *. The uncertainty determines the number of significant figures you should report in your final result. The last significant figure in the result should correspond to the first significant figure in the uncertainty. Example, if you calculate a value of 12.345 with an uncertainty of plus or minus 0.2, you should report the result as 12.3 plus or minus 0.2. You round the value to the same decimal place as the uncertainty. 6. Practice. Practice. The more problems you solve, the more comfortable you'll become with applying these concepts. 7. Example MHT set style problems. Let's look at some example problems that are representative of what you might encounter on the MHT set. Problem 1 *. The length of a rod is measured twice, and the values are 25.2 centimeters and 25.3 centimeters. If the standard length is 25.25 centimeters, calculate 1. The mean value of the length of the rod. 2. Absolute error in each measurement. 3. Mean absolute error. 4. Relative error. Solution *. 1. Mean value equals 25.2 plus 25.3, / 2 equals 25.25 centimeters. 2. Absolute error. First measurement equals 25.2 to 25.25 equals -0.05 cm. Second measurement equals 25.3 to 25.25 equals 0.05 centimeters. 3. Mean absolute error equals -0.05 plus 0.05, / 2 equals 0.05 centimeters. 4. Relative error equals 0.05 / 25.25 equals 0.00198 or 0.198%. Problem 2 *. The radius of a sphere is measured to be 5.0 plus or minus 0.1 centimeters. Calculate the surface area with uncertainty. Surface area equals 4 pi r superscript 2. Solution *. Problem 3 *. In an experiment to determine the density of a metal block, the mass is measured to be 100.0 plus or minus 0.1 g and the volume is 20.0 plus or minus 0.2 cubic centimeters. Calculate the percentage error in the density. Solution *. Problem 4 *. Two resistors, R1 equals 100 plus or minus 2 ohms and R2 equals 200 plus or minus 4 ohms, are connected in series. Calculate the total resistance and its uncertainty. Solution *. 8. Tips and tricks for MHT set. * Focus on the core formulas. * While the uncertainties library is powerful, make sure you understand the underlying formulas for error propagation. The MHT set may test your knowledge of these formulas directly. Practice with past papers. Solve as many past MHT set papers as possible to get familiar with the types of error analysis questions asked. Time management. Error analysis problems can sometimes be time-consuming. Develop strategies for solving them quickly and efficiently. Learn to estimate uncertainties when possible. Review significant figures rules. Knowing how to properly round and report results based on uncertainty is essential. Don't be afraid to approximate. In multiple choice questions, sometimes you can make reasonable approximations to speed up the calculations. 9. Advanced topics, beyond MHT set but good to know. Weighted averages. When combining multiple measurements of the same quantity, giving more weight to the more precise measurements. Covariance and correlation. When errors in two quantities are correlated, the error propagation formulas become more complex, requiring consideration of covariance. Statistical analysis using statistical methods like standard deviation, variance, and confidence intervals to analyze and interpret data. Monte Carlo simulations using computer simulations to propagate uncertainties by generating a large number of random samples. Conclusion. Error analysis is an essential skill for anyone involved in scientific measurements and calculations. By understanding the types of errors, the rules for error propagation, and practicing with examples, you can significantly improve your ability to solve problems and interpret experimental results. For the MHT set, focus on the core concepts, practice with past papers, and learn to manage your time effectively. Good luck.